We see how in the previous example that if we want to find a normal vector to a function like y equals the sine of x, we can cook up a function of two variables so that the graph of this y equals the sine of x is the zero level curve of this function of two variables. So anytime you have a function, you can bring either sine of x over to this side and you get y minus sine of x, or you can move y over to that side and you get sine of x minus y to get a function whose level curve at c equals to 0 is given by the graph of the function. So this graph here is one of the level curve of the function f of xy equals to y minus sine of x. And the other level curves will be around here and here, maybe for higher and higher c value. And over here for c equals to minus 1, c equals to minus 2, so on and so forth. So that level curve that we're talking about in function of two variable, in the function of three variable will be a level surface. So let's go to directional derivative for gradient for three variables. Just like the gradient for two variable, we have that the directional derivative is given by the gradient dot product the direction vector u. And so if the gradient vector is 0, then no matter which direction you're going, the gradient vector is the 0 vector, then no matter which direction you are going, the directional derivative will be horizontal 0. So then the direction of maximum increase will be given by the gradient of a function of three variables. And so the concept that we had earlier on of the normal vector to the graph is now going to be a normal vector to a surface. So this is a surface given by 4z equals to x squared by y equal 4x squared plus y squared. So it is the zero level curve of this three variable function. And so if you take the gradient of this function, then you will get a vector which is f sub x, f sub y, f sub z, given by differentiate this with respect to x, 2x, differentiate this with respect to y, 2y, and differentiating this with respect to z, negative 4. So this is the gradient. So if you want a normal vector pointing out of the surface, normal means perpendicular to the tangent plane, or perpendicular in general, if you know what that means, then all you have to do is find out what the coordinate of that point is, 2, negative 1, and 1, and substitute into here 2 whenever you see an x, and negative 1 whenever you see a y, and then 1 if there's a z appearing right here. So the gradient of f at the point 2, negative 1, 1 is given by 4, put this here, negative 2, negative 4. So you can see 4, negative 2, negative 4 is a normal vector to that surface. And this function here has a zero level surface equal to 4z equals x squared plus y squared, or z equals to a quarter x squared plus a quarter y squared. That is actually that parabolic surface over here. So the notion of having to create a function of more variables so that the zero level surface is this graph is very important because it helps us find the normal vector. And this is extremely important idea that we use to find the normal vector to help us build the equation of a tangent plane, or even the equation of a normal line, which is the subject of the next section, 13.7.